Okay, so thanks everyone for tuning in. Welcome to another Quantum Gravity and Information seminar. Today we're very happy to have Mark van Raamsdonk from the University of British Columbia, who's going to tell us about recent work on pushing boundaries in holography. So Mark, thank you very much and take it away.
Okay, so thanks a lot for the invitation and for giving me an excuse to get back to a normal, respectable waking schedule. So today I'm going to talk about various applications in ADS CFT where the CFT is living on a space-time with a boundary. And oops, okay, so just in general, if we have some conformal field theory, it's possible to think about that on various possible spacetimes. And in particular, we can have a spacetime with a boundary if we give a prescription for what happens to what is the physics at the boundary. And so for simple situations like a free scalar field, for example, we could choose Neumann boundary conditions or Dirichlet boundary conditions. But then even for more complicated CFTs, we have generally many choices of boundary conditions. And sometimes when I'm discussing these CFTs with boundaries in this talk, I'll also consider the possibility of actually adding a bunch of degrees of freedom at the boundary coupled in, and that could be part of what I'm calling my boundary condition. So in this talk, I want to focus on holographic theories. And so an interesting question is, suppose that I start with a holographic CFT, and now the space that the CFT lives on is equipped with this boundary. So that would be along this line. The holographic CFT is denoted in green. It's living on a half space. It has a boundary, and I want to know what does the gravity dual of that thing look like? So the original theory in its vacuum state would be dual to some gravitational theory in ADS spacetime. And now we just sort of cut the CFT in half, and so something has to reflect that in the bulk geometry. And so a basic picture that has emerged partly from this work of Karch and Randall long ago and Takayanagi is that we can imagine there's some boundary in the bulk space-time that extends into the bulk from the boundary of our CFT. So we're going to call this an end of the world brane. But you should think of that as kind of an effective prescription for what's maybe really going on microscopically in the bulk. And so we also have microscopic solutions for many situations. So for example, for n=4 supersymmetric Yang-Mills theory on a half space with some supersymmetry preserving boundary conditions, there are known solutions of type 2b supergravity. And so in the microscopic solutions, you don't have some explicit end of the world brane, but somehow from a lower dimensional perspective, you could still use a diagram like this to describe the situation. And what the end of the world brane represents is some region of the full geometry where the internal space maybe smoothly degenerates. And so one example that I find useful is to think about the bubble of nothing space-time, where you have a geometry with an extra circular direction. And then at some point in the large directions, if you move to the boundary of the so-called bubble of nothing, what's really happening is that circular direction is pinching off smoothly, but we would still maybe in the lower dimensional picture draw an end of the world brane to indicate the bubble of nothing. Okay. So we can try to treat the whole theory microscopically and find solutions of type 2b supergravity or whatever the relevant theory is. But to develop intuition and to work with relatively simple models, we can also take a bottom-up approach, as is common in ADS CFT. And the very simplest model that one can work with is to take this end of the world brane to be a purely gravitational object. Okay, so just like in the bulk theory, we specify an action for the metric and other bulk fields. We can specify an action in the bottom-up approach for the end of the world brane. And the simplest one is just to include a boundary cosmological constant or a boundary tension. And so that gives you one parameter in the model. Okay. And if I look at solutions in the simple case where my CFT is living on a half space, then what happens is that this end of the world brane, so let's say I've represented ADS space using Poincare coordinates. In this case, the end of the world brane just goes into the bulk at some angle, and the angle is larger for larger end of the world brane tension. So it's interesting to ask, what does that tension represent in terms of the physics of the boundary CFT? And Takayanagi made a nice observation a while ago that the tension of this brane is related to some measure of the number of boundary degrees of freedom. So there's a boundary analog of the central charge that comes in, and one place that it shows up is if you compute the entanglement entropy of, in this case I'm showing a 2D CFT, so I can imagine computing the entanglement entropy of an interval of length L, which includes the boundary of my CFT. And there's a universal result in CFT that this is equal to something proportional to the bulk central charge and the logarithm of the length of the interval, and then plus some boundary contribution. And this can be larger or smaller depending on my choice of boundary condition. So this quantity log G is called the boundary entropy. And what Takayanagi found is that is directly related to the tension of the brane when you do the same calculation using this simple, the simple kind of holographic model. And so the way you do that is using the Ryu-Takayanagi formula. And so we want to consider this interval, and then the RT surface, the RT surface goes up here and actually ends on this end of the world brane. And now that at first that may seem confusing because it doesn't look like this brane is homologous to that interval that I'm trying to calculate the entanglement entropy of. But we should remember in the microscopic theory, this end of the world brane represents just some interior points of the geometry. And so indeed the end of the world, the interval A together with this RT surface, those two together do provide the boundary of some region of our space-time, if you think of these as interior points. So indeed they're homologous. Okay. And so what happens in this calculation is that you have a certain region of the RT surface, this region up to the vertical dotted line here, that reproduces this part of the answer for the entanglement entropy. And then there's another part which is larger or smaller depending on that angle, and that's larger or smaller depending on the brane tension. And so you have this positive relation between the brane tension and the boundary entropy. Okay, so that will be important going forward, that the larger the boundary entropy, the larger this brane tension. And so, for example, in higher dimensional models, we can imagine trying to add a lot of degrees of freedom on the boundary. So for example, you can take n equals 4 super Yang-Mills theory on a half space and couple in some 3D superconformal theory with a lot of degrees of freedom. And in that case, well, there's some higher dimensional analog of this boundary entropy, and that would be large for that situation. And so then if we're trying to model that kind of situation, that would be modeled by having a large angle here. Okay, so at this point, I'll point out a little extension of that calculation that actually appeared yesterday evening for us, or this morning, I think, for everyone in Europe. So this was a paper with my postdoc Jamie Sully and my graduate student David Wakeham. So we were considering the calculation of entanglement entropy for a region, so again in 2D, but for a region A, which is not including the boundary. And so here, this is a situation kind of like the 2-interval case for a single for a regular CFT, where the answer in CFT is non-universal, but in gravity we can give a somewhat simpler answer. And so there's an interesting feature of this, which again is kind of parallel to the 2-interval case in in ordinary CFTs, which is that you get a phase transition. So using this gravity model, we predict that as you move the interval here closer to the boundary, you have a transition from a situation where the RT surface is connected to a situation where the RT surface is actually disconnected, as shown here. And so an interesting feature of the disconnected phase is that actually it again gives a universal result. So you see that the disconnected RT surface is just the sum of the two RT surfaces that we would use to calculate the entropy of B and the entropy of AB. And so the gravity calculation, even without knowing the details, so this is sort of a model independent observation, just using the fact that the RT surface is disconnected, the gravity calculation suggests that that the entropy of A should exactly be equal to the entropy of A union B plus the entropy of B. So it turns out that saturates a particular inequality for entanglement called the Araki-Lieb inequality when this interval is close to the boundary. And in the other phase, I should mention that the results in the really simple model where you have a purely gravitational end of the world brane, and we're talking about just a 1+1 dimensional CFT, then the result is simple because the bulk is locally ADS3, and we can calculate the answer for the entanglement entropy, and it doesn't really care that there's a boundary here. So you get this simple answer in that case. Okay, so we wanted to actually understand can we reproduce these things, this behavior from the CFT? And this is something that is, again, very similar to a paper that Tom Hartman wrote 7 or 8 years ago, thinking about the 2-interval case, and also on the gravity side, a paper that Tom Faulkner wrote. Okay, and so it turns out that you can understand this interesting phase transition on the gravity side, using a CFT calculation, if you make certain assumptions about the spectrum of the CFT and the behavior of CFT correlators. So if you want to do a direct CFT calculation of these entanglement entropies, then the standard approach is to use this replica trick. And so we first calculate Renyi entropies by evaluating the partition function for our model on a multi-sheeted surface where the surface is connected across this cut that's related to our original region. And so then in the CFT calculation, this calculation, as usual, turns into some correlation function, some 2-point function of twist operators. And now in the case of a boundary CFT, so 2-point functions are more interesting than 2-point functions in regular CFTs. Their form is not fixed by symmetry. And there's actually, so similar to a 4-point function in regular CFTs, there are actually a couple of different channels that we can expand the 2-point function in. Okay, so this 2-point function of the twist operators in our boundary CFT, there's a bulk channel where we take the bulk OPE of those two, and then you end up taking a 1-point function of this bulk operator OI. Okay, so we can represent the 2-point function this way as a sum of these 1-point functions. Or there's also a boundary channel where each of the twist operators is expanded in terms of boundary operators. There's something called the boundary operator expansion. and we end up taking the 2-point function of boundary operators. And so what we found was that the results from our gravity calculation using this simple model actually were exactly reproduced if you simply keep only the vacuum block in the bulk channel. That gives this result here, and if you keep only the vacuum block in the boundary channel, that gives this this universal result here. Okay. And so now I should remember this result is sort of specific to the particular model. If you have more complicated couplings of this brane to the bulk fields, then you can have, say, scalar fields turned on, back reaction, and you'll get a different result here. And so the gravity picture suggests that this sort of vacuum block result is probably not typically the full result in the CFT calculation. On the other hand, the gravity side does predict that this result is universal, and so that suggests that there generally will be this vacuum block dominance in the calculation when you go to the boundary channel. Okay. So that's sort of the direct CFT calculation of these entanglement entropies. There's actually a third way you can imagine doing the calculation. Oh, yeah. Question.
Yeah,
please.
is there some argument within the CFT, given something about the spectrum, that the vacuum block on the boundary really does dominate?
Yeah, that's a good question, and so we analyzed that, and so given a certain sort of sparseness condition, which we wrote down in detail in our paper, then you can argue that the vacuum block does dominate. So basically, similar to Tom's old calculation, if the spectrum of these boundary operators doesn't grow too fast, then you will have vacuum block dominance. So it's, yeah, so you kind of get a prediction from the gravity about the spectrum, the density of states in this CFT. The third way that you can imagine doing this calculation is to use the replica trick, but then imagine doing the calculation of these multi-sheeted partition functions using a gravity calculation. And so that's similar to what Tom Faulkner did for the 2-interval case. And there's actually an interesting feature here, which is that when you think of the gravity calculation for so you find a solution of the gravitational equations whose boundary is this replica manifold. So in this case over here, when the interval is far away from the boundary, in the gravity replica calculation, you have end-of-the-world branes ending on these CFT boundaries, which are disconnected from each other. And when you move closer, then you have end-of-the-world branes that are all connected together, and so this is like this is what we would call in modern language a replica wormhole. So the end of the world brane geometry is a replica wormhole, and later in the talk we'll be connecting this observation to other things people have said recently about replica wormholes in the context of black hole evaporation. So this is a good point to stop and see if there are any more questions before I get on to various applications. Okay. Okay, so I want to talk about how using these CFTs with boundaries allows us to do some interesting new things in holography that are not as easy, at least using ordinary CFTs. And so my first kind of key point is that using boundaries for our CFTs allows us to consider bulk spacetimes where at least part of the boundary of that bulk spacetime is dynamical. So this is kind of a big issue in ADS CFT. In usual examples of holography, we're kind of restricted to spacetimes where the boundary geometry is some kind of rigid, has some kind of rigid asymptotic behavior, either asymptotically ADS or some other fixed asymptotics if you're thinking about a non-conformal dual theory. And so, of course, we would like to be able to study spacetimes that are more general, where maybe the boundary is dynamical. There's been some interesting progress in that direction with the TT bar deformation recently. But I also wanted to point out that if you have boundaries in your CFT, then at least part of your boundary can become dynamical in the gravity picture. And so this is kind of indicated by this cartoon here. This is standard CFT dual to ADS spacetime. And now I want to imagine the same CFT, but just remove a hole and place a boundary condition at the edge. And so now what happens is that the dual geometry has to reflect the fact that we've inserted this boundary into our CFT, and that's going to, according to our general picture, involve some end of the world brane. Okay, but in this case, when the boundary is circular, this end of the world brane just sort of smoothly closes up, and so and so we have, part of the space-time where you have asymptotically ADS, but then there's this other part here in the middle where you would have, say, some finite distance to the boundary, and then the boundary physics is dynamical. Okay. So that's sort of an interesting new feature that we're able to study using these CFT boundaries. We can understand something about a part of space-time with a dynamical boundary. Okay, so I should mention that this is sort of reminiscent of the old work of Randall-Sundrum, who were thinking about asymptotically ADS spacetimes, where instead of a rigid asymptotic boundary, you have what was called a Planck brane. That was like a cutoff surface in your ADS space close to the boundary, and so they understood that you can have gravity localized to this Planck brane, and so using ADS space, you have this interesting possibility of defining. So with ADS D+1, you can define some d-dimensional gravitational theory where you have gravity localized to the Planck brane, and this gave interesting possibilities for phenomenology and cosmology.
Excuse me, Mark.
Yes.
It's Lenny.
Hey, Lenny.
As you make the circle bigger and bigger, the end of the world brane goes deeper and deeper into the geometry?
Yeah, so in this case, the circle would be in this picture, the circle would be the only scale, the size of the circle would be the only scale. And so,
so you can't keep the brane close to the boundary, so to speak, or some fixed
well,
distance.
I'm going to tell you how to keep the brane close to the boundary.
Okay, good. Thank you.
So the key thing is to remember that, let me go back a few slides. The key thing is to remember that in this simple picture, there was this angle here, and the angle depended on how many degrees of freedom that you had on the boundary. And so what I want to do to keep the brane close to the boundary, I want to make this angle big. So I want to add a lot of degrees of freedom. And so that's the picture here. So if I take well, this is the 2D version. If I take the boundary entropy to be large relative to the measure of degrees of freedom in the bulk, then this brane, actually I want to use my hands. There we go. Okay, now you can see. So then what happens is this, I don't know if you can see my face, but I'm doing this thing with my hands. So then the brane comes closer and closer to the boundary because the angle here gets smaller and smaller. Okay.
Good. Thank you.
Sure.
So Mark?
Yeah.
Are there gravitational degrees of freedom then that are dynamical at this boundary? It's a little confusing. So, right. So as you said, the reason that Randall-Sundrum was one of the reasons it was interesting was that you and people are interested in these sort of like cutoff ADS models is that there's some gravitational degrees of freedom because you have an ADS cutoff that are now normalizable and can fluctuate.
Yes.
So, but it doesn't seem like there is such a degree of freedom in your boundary degrees of freedom, or are you allowing the possibility that your boundary theory, your end of the world brane has some gravitational degrees of freedom living on it?
Yeah, so I think you should think about there being gravitational degrees of freedom. I mean, first of all, the brane is fluctuating, so it has a dynamical metric. But what I want to argue is that this picture here is indeed just like the situation people were talking about, where you can have some effective description, which is a lower dimensional gravity theory living on that brane. So I want to suggest that kind of like in the Randall-Sundrum days when people were saying that you have sort of a cutoff CFT coupled to a gravitational theory, that's indeed the description here, that you have some region of space where you have your original CFT, and then you have this region of space which I've now filled in, which is effectively described by the cutoff version of this CFT. So you in the bulk you have these degrees of freedom going out to the brane, but not all the way to the ADS asymptotic boundary. So you have a sort of a cutoff version of that CFT, and then that thing is coupled to a dynamical gravitational theory in this region. Okay, but I'm going to tell you what that theory is. Remember that we put a whole bunch of we put a whole bunch of degrees of freedom on this circle. Okay, so if we think about those as being some lower dimensional holographic theory, I mean, let's say this CFT is a 2D CFT and the circle is one dimensional. Then you can think of the one dimensional theory as with a lot of degrees of freedom as being dual to a 2D gravity theory. And so that would be the gravity theory that is coupled to the cutoff CFT, which is related to the original CFT.
Okay.
So another way to think of this whole picture is that, let's just start with a one-dimensional, the boundary theory. Let's start with a holographic theory on a circle. That has a gravity dual which sort of fills in the circle. So that's the pink region. And now we're going to couple that whole thing to this bulk CFT. But the number of local degrees of freedom of that bulk CFT is sort of small compared to the number of degrees of freedom here. And so in a sense, you could think of that as being, a small perturbation. So you're adding this extra dimension, but there's still physics of a, in this case, 2D gravity theory there that is maybe not so much disturbed by the fact that there's this higher dimensional gravity physics being added on. Okay, of course, adding a new dimension is probably not a small perturbation in some sense.
Mark, I have a question which is related to what you're describing now. It seems that you're suggesting that the part of the boundary that is outside the region in which your theory is living is interacting with what happens. But that doesn't seem possible, is it? Like what I'm saying, or what are you really describing? So,
I mean, from the gravity perspective, there's this sort of dynamical end of the world brane that's interacting with the metric in the rest of the space-time.
But then you need to put boundary conditions outside the region where your quantum field theory lives in the boundary. And what do these boundary conditions correspond to?
You mean I need to? Sorry, you mean I need to put boundary conditions here in the gravity picture, or maybe I haven't understood your question.
No, in the boundary, you have a region where your theory lives and a region outside it, right?
So I have, so my microscopic theory is a CFT living on this space outside of the circle. And then maybe there's some extra degrees of freedom here living at the edge, and there's nothing in the middle.
Oh, I see. So it's just the opposite. I'm sorry. Now I understand. Thank you.
Okay. Okay. Okay, so with this picture, actually, there's an interesting application. So the picture that I drew here, where you have a cutoff CFT coupled to gravity in some region, and then a CFT outside that with fewer degrees of freedom. This is actually very similar to some models of black hole evaporation that were discussed by these people. So in particular, it's similar to a certain model involving JT gravity discussed by Almeri, Majan, Maldacena, and Zhao, where they wanted to study the evaporation of a black hole by coupling a gravitational system to a non-gravitational system, and they wanted to take their entire system to be holographic in a sense. And so that's actually exactly the situation that we have here. And so in this paper from the fall with Moshe Rosali and Jamie Sully and David Wakeham, we thought about using these boundary CFT type models to give examples of where we can study black hole evaporation and page curves and so forth. So the idea here is that we want to, again, start with our model where we have a boundary here with a lot of degrees of freedom. And then, so one way to think of this is, again, by just imagine starting with that boundary theory. So that could be on a circle or a sphere in higher dimensions. Imagine putting that boundary theory into a high energy state. And so that would describe some black hole in an asymptotically ADS spacetime. But now we couple in these bulk CFT degrees of freedom. So that's like our auxiliary radiation system. And then what can happen is that the energy now can leak out from this black hole space-time and end up in, or from the original boundary degrees of freedom, end up in the bulk degrees of freedom. And so the gravity picture is that our black hole is going to evaporate. And an interesting feature here is that just a really simple kind of CFT calculation using sort of the Boltzmann law. If you estimate how long it takes for the black hole to evaporate, then it's controlled by the ratio of the number of bulk degrees of freedom and the number of boundary degrees of freedom. So if you have relatively few bulk degrees of freedom here, then it takes a long time for the black hole to evaporate. And so you predict a page time, which is proportional to the log of proportional to the boundary entropy over the bulk central charge. Okay. So sorry, we can use this kind of effective description. So there's now going to be three pictures. So our microscopic picture is just, we have a bunch of energy sitting in these boundary degrees of freedom at the start. Then there's this effective description, which says that you have a black hole in your effective gravity theory that fills in the circle or the sphere, and then that thing is radiating. Normally, the radiation would just bounce back from the boundary, but in this case, it's coupled to this CFT, so the radiation can escape. Oops. Here we go. And so what we can do is kind of probe the entropy and the Hawking radiation in this auxiliary system. So this shaded region A is just a large portion of my bulk CFT. And what I want to imagine doing is calculating the entanglement entropy of that region A as a function of time in order to study the entropy of the radiation system. Okay, now what we actually did is something a little bit simpler. Okay, so first of all, in order to make the calculations as simple as possible, we studied a version of this where the CFT was just one-dimensional. Okay, so instead of a one-dimensional sphere here, we have a zero-dimensional sphere, so just sort of 2 points. And then the bulk CFT is one-dimensional. So to get a black hole, we still put this into some thermal state. And again, you could, so in the thing I described previously, I was thinking of putting a bunch of energy into these boundary degrees of freedom and then having the energy leak into the bulk. But actually we realized that it's simpler just to have everything be in thermal equilibrium. So you start with the thermal field double of your entire theory over here with this entire theory over here. And so then the energy density doesn't evolve at all. But there's still an interesting evolution of entanglement, it turns out. So actually these people also kind of pointed out the same thing in a paper at the same time. So what we're going to study is just the entanglement entropy in a situation where nothing is really changing from an energy perspective. We're still, sorry, let's just want to annotate this. Yeah, okay. Okay, so we have this state which is initially the thermal field double state, and then we're just going to track the entropy of this combined region A and A as a function of time. Okay, and so as emphasized by these people, even in this kind of the simple situation, which is static from an energy perspective, there's an information paradox, and a way to see that is that if you just calculate the entropy of the radiation system as a function of time, using kind of a naive holographic calculation. Okay, so let's set this up a little bit. So using some naive holographic calculation, the entropy of the radiation just goes up forever. But then using a correct calculation, you see that the page curve eventually stops increasing and flattens out. Okay, so let me set up the gravity picture of our calculation. Okay, so basically this picture shows the full Lorentzian geometry. A way to understand that is that if you just started with the thermal field double state of these boundary degrees of freedom, so that would give you some 2D black hole, and that's sort of indicated here by this red portion of the full geometry. Okay, and then there's a higher dimensional bulk geometry, which is related to the bulk CFT. Okay, so if we didn't have these boundary points, if we just had a bulk CFT coupled to another bulk CFT in the thermal field double state, then that would give us some planar black hole geometry, which is sort of stretching out here. Okay, so this is our full bulk geometry, and now this region here. So this region here, A, is this right here. So at time equals 0, and then over here, the other part of the region A is over here. And so what we want to calculate the entanglement entropy holographically is to find an RT surface whose boundary is the union of these 2 points. Okay. And the simplest RT surface is just stretch across. So there's one in some set of coordinates. You have an RT surface that's just literally a line from one side to the other. And as a function of time, there's sort of these related RT surfaces. Okay, so I've got this sophisticated animation here. Okay, so if I calculate the RT surface as a function of time, then you have this series of extremal surfaces, and if I take the entropy from that calculation, it just seems to go up to infinity. Okay, so that's a version of the information paradox, that you have this initial black hole with a finite entropy, and it radiates into the radiation system, and somehow it seems to have radiated an infinite amount of entropy. But the resolution is that there's another set of RT surfaces. And so instead, at some point, what you find is that there's this disconnected RT surface that actually ends on the end of the world brane, and and then there's a family of those that turn out to be the correct RT surface, the least area RT surface for later times, and so you get a resolution of that information paradox because your entropy now reaches some finite maximum and doesn't go above that. Okay, and so the interpretation, and so right. One of the interesting things that, so this is something that, you know, originally was, pointed out by this list of, okay, all of these people. So, you know, that's sort of not new.
Mark,
Yeah.
can I ask a question?
Yeah.
I've been sitting here thinking that you're talking about something different than you are. You're not talking about evaporation. You're talking about the two systems coming to thermal equilibrium with each other. Is that correct?
Yeah. So instead of talking about evaporation, what I'm talking about is
the equilibration.
Starting, I mean, they're actually kind of in equilibrium. So I'm starting in the thermal field double state.
Yes.
So in a sense, everything is in, both sides are thermal states.
Right, but the red dots are not yet coupled.
But the red dot is sort of now sharing information with the green line.
Yeah. Okay.
So, yeah. So, sorry, what's happened here?
So it's a thermofield double where the thermality is just in the red dots?
No, it's the thermofield double of this entire system here with this entire system here. So, you know, it's like a black hole, but there's already radiation here, and these two are kind of in equilibrium in the sense that there's not going to be any transfer of energy from here to here. But I guess in the original state, in the original state, these degrees of freedom are kind of entangled with these degrees of freedom, and these black hole degrees of freedom are entangled with these ones. Yeah. And then what happens as a function of time is that now the entanglement is more between the black hole and the radiation. Okay, so it's first.
So why are you reluctant to say that the red region is coming? The reds are coming into equilibrium with the green.
Yeah, I would say that. I'm just saying from a thermodynamics point of view, normally coming to equilibrium usually involves some flow of energy one way or the other, and this is more of a scrambling kind of information type equilibrium.
Can I make a comment?
Good.
Yeah, go ahead.
It's Raghu. So you can think of it as a Hartmann-Maldacena kind of evolution where you evolve the two sides both forwards in time. Yeah. That's the thing that's causing the time dependence.
That's right. Yeah, that's right.
But then why is this a thermofield double, right? What shouldn't you be in energy eigenstates of the coupled system?
Well, the thermofield double is, so again, like as Ryu just said, we're thinking about the forward time evolution on both sides. So that the thermofield double is not an energy eigenstate for H1 plus H2. And, you know, in particular, like the distance across the black hole here gets larger as a function of time. And we see the entanglement entropy is evolving with time. Yeah. So, I mean, the basic picture is what I said, that in the thermofield double state, you have entanglement between these degrees of freedom and between these degrees of freedom, and then sort of local entanglement in your field theory. And then you let it evolve forward in time on both sides. And now the black hole degrees of freedom become more entangled with the other CFT degrees of freedom that they're coupled to. And
Mark?
so eventually, you know, this
Mark,
transition is yeah.
Can I have a question?
Yeah, sure.
Is there so over here you have a parameter that is number of degrees of freedom of the boundary and number of degrees of freedom in your CFT.
Yeah.
Is there some interesting transition between what's happening depending on what's the ratio of these numbers?
Absolutely. So you know, this turnover, one of the interesting things about this model is this turnover happens at a time which is exactly controlled by that ratio. So the turnover happens at this time, which is the ratio of boundary degrees of freedom to bulk degrees of freedom. that's the page time for our model, and that was what we suspected based on the simple calculation.
Yeah, thanks.
Okay. I'll just point out one feature that is very interesting about these calculations is that after the transition, if you ask about what is the entanglement wedge of the joint region A and A, then the entanglement wedge now includes some portion of this black hole system, which is indicated in blue here. And so from an information point of view, we see that after this transition, what happens is that you have enough information in the radiation system to reconstruct this portion of the black hole interior. Okay. Okay. Okay, so one of the things I wanted to now point out is that we can actually understand all of this from a CFT perspective as well. So it's, oh, I see, I think there's a bunch of chat messages.
Yeah,
okay, so
if people in the chat are just doing that to ask questions to each other, then I guess that's fine. But if you want to actually like participate in this discussion, then unmute your mic and speak up, because we don't really see the chat. It doesn't get recorded, etc.
Okay.
So please speak
yeah,
up
if you have a
want
question,
to
let
say
me know.
something. Otherwise, it's distracting.
Okay, let me just point out what the CFT version of this calculation is. And so here, this lower half you can think of as a Euclidean path integral that generates the thermofield double state of my two theories. And then the calculation of entanglement entropy that I want to do involves this region indicated by the cuts. And so the calculation I just mentioned of entanglement entropy in this thermofield double state is related to this particular CFT calculation where you have a boundary part of the space-time and then cuts, and we want to go ahead and calculate the multi-sheet partition function. And so it turns out by a conformal transformation, this thing maps to this. And so actually, again, the calculation that we need to do here is just related to this calculation of a two-point function of twist operators in a boundary CFT. And so the phase transition that sort of leads to this this transition in the page curve, it's exactly the same, kind of has exactly the same origin from the CFT perspective as this phase transition that we showed earlier, sort of an exchange of dominance from the bulk channel to this boundary channel. Okay, so I want to move on to a last application. Actually, I don't have the time here. What is the time currently?
It's 10 till, but I mean, you know, it's not like we're going to get kicked out of the virtual room. So, you know, it's a soft
okay,
cutoff.
yeah, let me go quickly through this last application and then, okay, so, right, so one of the interesting things so far is that we have these dynamical boundaries of space-time. So far, those things were kind of anchored on our actual ADS boundary. So the end of the world brains themselves, or these Randall-Sundrum Planck brains, they sort of had asymptotically ADS geometries, and they were kind of attached to our boundary. The next application asks whether we can have a situation where these same end of the world brains can exist, but without a boundary. So this is sort of maybe a toy model for an interesting direction in ADS CFT, which is that obviously we want to be able to describe cosmological spacetimes eventually in quantum gravity. So it's interesting to ask, well, can we do this first with end of the world brains, maybe even ones that have localized gravity? And so so the interesting trick in order to do that is to add boundaries to our CFT, but not in the actual CFT that we're studying. We could add a boundary in the Euclidean past. And so this was work with various people at UBC, motivated by a paper of Kurkulu and Maldacena. Okay, so I'll just very quickly review this. Maybe people have heard it before, but there's a little bit of new material that I want to talk about. So the idea here is I want to study states of a CFT on a sphere where, so here's the CFT on the sphere, and I define a wave functional for that theory as a Euclidean path integral over all the configurations of fields on this cylinder, where I put a boundary in the Euclidean past. And so possibly adding these boundary degrees of freedom here in the Euclidean past, they get integrated over in my path integral. And so that ends up defining a particular state of this CFT, of just the ordinary CFT on the sphere. And so then we can understand, what is the Lorentzian geometry that's dual to that solution? Okay. And as a first step, we can first find a Euclidean solution that we would use, say, to calculate correlation functions in this state. Okay, so that would be some Euclidean geometry, which has a boundary that has this half cylinder and then another half cylinder corresponding to the bra. And in the Euclidean geometries, you have an interesting transition where for large values of this, this Euclidean time parameter, you have end-of-the-world branes that are disconnected from each other, and your bulk kind of looks like vacuum ADS. But for small values of this tau zero parameter, which turns out to correspond to high energy states, you have end-of-the-world branes that are connected. And actually, in modern language, the end-of-the-world brane geometry we would say is a Euclidean wormhole. Okay. So that's the Euclidean picture, but the Euclidean geometry is related to the Lorentzian geometry. We can think of the tau equals 0, the time equals 0 slice, as providing some initial data for our Lorentzian spacetime. And so if I focus on this latter picture, the high energy case, and I look at the time equals 0 slice, if I'm a little bit more careful and work out the metric, then it just looks like a black hole geometry. And this end of the world brane, it turns out, is behind the horizon. As long as the tension of that thing is positive, it ends up behind the horizon. And so you have these interesting CFT states that correspond to black hole microstates, but you actually have some specific behind the horizon geometry that you could work out, and the whole space-time ends in the interior, in an interior boundary on this end of the world brane. Okay. Now that thing has interesting dynamics. So it's a closed end of the world brane. It has interesting dynamics. This is what the whole thing looks like on a Penrose diagram. So you have a portion of the two-sided black hole where the interior boundary, so this red line, is our end of the world brane. It comes out of the past horizon, it goes into the future horizon and ends at the singularity. And so the geometry of that thing is a big bang, big crunch type cosmology. And so, in order to get, of course, that's just the geometry of the boundary of our space-time, but it's quite interesting to imagine the case where you have a lot of degrees of freedom here and where this boundary is pushed close to the ADS boundary on the other side. In that case, it may be possible to have a situation where you have localized gravity, where this end of the world brane is actually like a Randall-Sundrum brane, and where you then would have a model of Randall-Sundrum cosmology. Okay, let me sort of skip this part. Okay, just very quickly, so the summary is we have this just a state of an ordinary CFT, which encodes the physics of this interesting behind the horizon time-dependent end of the world brane. An interesting question to ask is, how do you actually probe that physics using the CFT? One way to do it is again using entanglement entropy, just looking at the entanglement entropy of large enough regions of the CFT actually
Sorry,
probes
Mark, I have a question.
Yeah.
So inside this red spindle thing, are you imagining there is something living, or is it empty?
So it's empty. I mean, I imagine this thing represents the interior boundary of our black hole. Okay. So you go inside the black hole and then you hit the end of the world brane, there's nothing behind it.
Okay, thanks.
Okay. Yeah, so the short thing was that you could probe behind the horizon here using using entanglement. We find a similar transition where beyond the transition point, the entanglement wedge of your this portion of the CFT extends behind the horizon and includes part of the end of the world brane. Okay, so that's what the entanglement entropy looks like as a function of subsystem size. That graph looks sort of familiar, and it's because, again, you can do a CFT calculation of this. So here's the CFT calculation that you want to do, and again, it's very closely related to the calculation that we did before. Again, it's related to a 2-point function of twist operators in a CFT with a boundary, and the understanding of this phase transition that allows you to see behind the horizon of the black hole is the same as before. Okay. So the last thing I wanted to point out, and this wasn't in our paper from a few years ago, so that's why it's a modern perspective, because it's taking into account some of the many recent works on Euclidean wormholes. And so one of the interesting things that has been discussed recently is that Euclidean wormholes seem to arise in very simple models of quantum gravity when you have ensemble averages of theories. And people have asked, is this ensemble average picture relevant for ordinary holography? And so, so here's a situation in ordinary holography and whatever number of dimensions you want, where what shows up is a Euclidean wormhole, but it's a Euclidean wormhole of your boundary degrees of, related to your boundary degrees of freedom. It's an end of the world brane Euclidean wormhole. But an interesting point is that this Euclidean wormhole, it turns out, if you think about it in the right way, it does arise from an ensemble average. Okay. So, sorry, this slide is a bit technical. So here was our calculation. We were thinking about this partition function of a theory with a boundary in the Euclidean past, and here's a boundary in the future. Here's our bulk CFT. And this thing we said was dual to the space-time with this Euclidean wormhole if this parameter tau 0 was small enough. And so now what I want to do is I want to imagine this theory as really 3 theories coupled together. Maybe I have some bulk theory here on a cylinder with a simple boundary condition without many degrees of freedom. And now I'm coupling in some extra boundary degrees of freedom by adding a coupling between the operators here and some boundary operator here. Okay, and I want to compute the entire partition function of this theory. Okay, so that has an integral over bulk fields and over boundary fields, and then you have your actions for the bulk theory and for the 2 boundary theories, and then you have these couplings. And so it turns out that I can sort of formally rewrite this whole thing by defining a probability distribution for sources. Okay, so I think of the expectation values of these these green operators as, so see these green operators here from the bulk theory are showing up as sources for these red operators that are in the boundary theories. Okay. And I can think of my bulk CFT as just generating a probability distribution for these sources. So formally, if I define this joint probability distribution of these sources using my bulk path integral like this, then I can rewrite this whole partition function, like this. And that is exactly an ensemble average of the product of these 2 partition functions for these 2 boundary theories. Okay. And so we now have a different way to understand the appearance of this Euclidean wormhole. In the case where tau 0 is large, then that would mean that there's going to be weak correlations between the sources in this joint probability distribution. And that seems to correspond to a disconnected end of the world brane. Whereas if I have a small value of this T0 parameter, that will correspond to stronger correlations between the sources in this joint probability distribution. And that seems to be the situation where we get the end of the world brane. Okay. And so it's interesting then, in this different viewpoint, you can think of the bulk CFT as generating this joint probability distribution for the sources. But then the final result can be expressed just in terms of that probability distribution. So from the point of view of these two boundary theories, what you have is some ensemble average of two partition functions, and then that seems to be dual to this end of the world brane with a Euclidean wormhole geometry if the sources are correlated enough. Okay, so that seems to be very interesting, especially because there's this connection to cosmology in our setup. The tau equals 0 slice of this thing gives some initial data for Lorentzian Big Bang cosmology. And so, I guess the takeaway here is that in some sense, these ensemble averages are definitely relevant to ordinary higher dimensional holography and lead to the appearance of Euclidean wormholes. Maybe this is a hint for how we could do holography, or how we could do cosmology more generally using holography. It's interesting to ask, is the bulk CFT really crucial here, or could we have just started with two ordinary holographic theories and integrated, introduced some other kind of joint probability distribution for sources? Are there other examples where you get some nice geometrical interpretation? Okay, and so I guess this is a good stopping point. So we've added boundaries to our CFT, and it's given us these various new tools in holography. And I think I will stop there for this talk.
Okay. Thanks a lot, Mark. Very good. The applause does not work quite so well in the virtual format. I apologize. We've got plenty of time for questions. If anyone wants to continue the discussion, please speak up. We had quite a few already.
Hi, Mark. I have a question.
Alex.
So I was wondering what's known about the spectrum of boundary states. Say, you pick some typical boundary state. Is it clear, for example, that the only operator that has a large VEV in that state is the stress tensor?
Yeah, so I think there's not very much known. In minimal model CFTs, then we know what the possible boundary conditions or boundary states would be. But for holographic theories, I think relatively little is known. And I would say your question there about 1-point functions, I don't think it's true in general that some holographic theory with a boundary will only have 1-point functions for say the or we'll have just this purely gravitational end of the world brane. That sort of simple model. I think certainly in the microscopic examples that we have, where you have solutions of type 2b supergravity corresponding to n equals 4 with some boundary conditions, then you have other scalar operators in the n equals 4 that have 1-point functions. And so the full geometry has some scalar fields turned on and back reaction. I kind of think of this simple model with the gravitational end of the world branes as just being the simplest kind of bottom-up model that you can work with to develop intuition for how these things are going to work more generally.
So if you have 1-point function for other operators, does it mean that viewing it as a one-sided black hole, you sort of want to think about it as having also matter falling in?
Yeah, absolutely. So these are time symmetric, and so they would be something where what you would see in the past is actually maybe some scalar fields coming out of the black hole. But if you start at time equals 0, then you have some scalar fields turned on outside the black hole, and then they would just fall into the black hole. And in the late time physics, you would have a black hole, ordinary Schwarzschild black hole.
Awesome. Thanks a lot.
I have a question.
Yes.
You can think of a quantum field theory with a boundary, and then you can just prescribe boundary conditions like Dirichlet or Neumann. Or you can put a lower dimensional quantum field theory on the boundary and then specify its action and how it couples to the bulk quantum field theory. Do you expect in these two different cases a qualitative difference between the what happens at this, or how the end of the world brane behaves?
Yeah, I mean, I think so far we have this crude model where we only have one parameter for the end of the world brane, and it's related to just this boundary entropy. And so I think in that case, the more degrees of freedom I couple into the boundary, the larger that boundary entropy is going to be. But even with like Dirichlet boundary conditions or Neumann boundary conditions, it turns out there can be different values of that boundary entropy. So at this point, so far, it's just, in the end, whatever you do, if you choose some boundary conditions, you couple in some extra degrees of freedom, then there is this one parameter that you can calculate from the field theory point of view. You can calculate this boundary entropy, and then that will feed into the tension in the simple model. Now, as I sort of alluded to discussing with Alex, so another thing, so maybe the next property you can look at in these boundary CFTs, you can look at one-point functions of scalar operators. So those can be non-zero. And if I have a one-point function of some light scalar operator, that suggests that on the gravity side, there should be some scalar fields turned on in my geometry. And a way to incorporate that into the bottom-up kind of models is to just simply have a coupling on your end of the world brane, which is linear in some bulk scalar field. So like an integral of the square root of the boundary metric times a scalar field. That will give a source for the scalar field on the end of the world brane, and eventually that would reproduce some one-point functions in the CFT. So you can think of coming up with more detailed probes of your boundary conditions. Depending on what your choices are, you'll have different one-point functions for various operators, and then you can incorporate that into your action.
Thank you.
Other questions? Okay. Well, if there are no other questions, then let's thank Mark again for this very interesting talk. Thank you.
Thank you.
Okay. Thank you all.